Today, we're diving deep into the hidden world of light. We're going beyond what we can see, into the quantum realm, a place where light gets really, really weird. And it turns out that weirdness is the key to unlocking everything, from totally unhackable communication to seeing the echoes of black holes colliding across the universe. So let's jump in. First things first, to really appreciate where we're going, we have to understand where we've been. For a long, long time, we thought we had light pretty much figured out. But that old classical view, well, it was missing the best part of the story. And here are the two realities, side by side. On the left, you've got the classical view. Light is predictable, it acts like waves in a pond, it's neat, it's tidy, it makes sense. But then you look at the right. That's the quantum view. Suddenly, light is probabilistic, it's all about chance, and it has these properties that are so bizarre, Einstein himself called one of them spooky action at a distance. So how in the world do we make sense of all this spookiness? Well, that's where a field called quantum optics comes in. Think of it as the new rule book, the physics that gives us the framework to not only understand these weird properties of light, but to actually harness them. Okay, to understand the new rules, we've got to meet the star of the show. Let's talk about the fundamental particle of light itself. Say hello to the photon. This is the smallest possible packet of light you can have. And right out of the gate, it's a rule breaker. It acts like a tiny, distinct particle, like a little bullet. But it also acts like a wave, spreading out in space. And it's not one or the other, it's somehow both at the exact same time. This wave-particle duality isn't just a fun fact, it is the foundation for everything that comes next. And the photon doesn't travel light, it comes with this amazing quantum toolkit. You've got superposition, which lets it be in multiple states at once, kind of like a spinning coin is both heads and tails until you slap it down. Then there's entanglement, which we'll get to, where two photons are mysteriously linked, and quantization, which just means light comes in these discrete chunks. You can have one photon or two photons, but you can never, ever have 1.5. It's these rules that turn light from just something we see with into a revolutionary tool. Okay, so it's one thing to know these bizarre rules exist, but the real question is, how do you actually use them to build something real? Well, believe it or not, you're probably way more familiar with the answer than you think. The single most famous piece of technology to come directly out of quantum optics is the laser. Lasers work because of this really beautiful quantum process called stimulated emission. It's basically a chain reaction. First, you pump a bunch of energy into some atoms, getting them all excited. Then, a single photon just happens to fly past one of these energized atoms. And here's the cool part. It doesn't get absorbed. Instead, it triggers that atom to release a second photon that is a perfect identical clone of the first one. Same direction, same frequency, everything. Now you have two photons, and they go on to trigger more atoms, creating a cascade that amplifies into that powerful focused beam of light we all know. It's a perfect quantum copy machine. All right, from the focused power of a laser, let's jump to probably the most mind-bending quantum idea of them all, and see how it's being used to create perfectly secure communication. This is photon entanglement. The idea is you can create a pair of photons that are fundamentally linked. Their fates are intertwined. So if you measure a property of one of them, like its polarization, you instantly know the state of the other one, no matter how far apart they are. And when I say any distance, I really mean it. This isn't just a theory in a lab. Scientists have proven this instant connection works over hundreds of kilometers, even between satellites in orbit and labs down on Earth. It's absolutely real. Okay, so an instant link across space is incredible. But what can you do with it? How does that spooky action actually lead to something as practical as unhackable communication? The answer is something called quantum key distribution, or QKD. Here's the genius of it. Let's say we're sharing a secret key using our entangled photons. In the quantum world, the very act of looking at something changes it. So if a hacker tries to intercept our photons to steal the key, the moment they measure one, that measurement disturbs the whole entangled system. We would see that disturbance instantly on our end and know someone was listening in. The very laws of physics become your security guard. All right. Next up is an application that's just as profound. This one involves manipulating the randomness, the actual uncertainty that's baked into the fabric of reality itself. See, at the quantum level, things are never perfectly still. There's always this fundamental background noise or fuzziness. But with quantum optics, we can actually get in there and control it. We can manipulate this quantum noise, quieting it down in one place to get a much clearer signal. This is called creating squeezed states of light. But as you know, there's no free lunch in physics. The Heisenberg uncertainty principle says there's always a trade-off. We can squeeze the uncertainty out of one property of light, making our measurement of it incredibly precise. But all that uncertainty has to go somewhere, so it gets pushed into another property, making that one fuzzier. Think of it like squeezing a water balloon. If you make one part narrower, another part has to bulge out.
So why on earth would we do this? What's the payoff for this quantum balloon squeezing? Well, it's nothing less than hearing the universe whisper. By using squeezed light to reduce that quantum noise, instruments like LIGO can make measurements so ridiculously sensitive that they can detect the tiny, tiny ripples in space-time itself, gravitational waves, that were created by two black holes colliding a billion light years away.
So where is all this headed? Let's look to the future, because these principles are laying the groundwork for the next generation of computing, and for how we even understand reality. So instead of using electrons to represent the ones and zeros in a computer, we can actually use photons. A single photon, thanks to its ability to be in a superposition of states, can act as a qubit, which is the basic building block of a quantum computer. And building computers out of light like this could have some huge advantages. We're talking about potentially incredible processing speeds. They would also use a lot less energy than our current electronics. And on top of that, photons are naturally more robust against certain kinds of errors, which makes them a really promising way to build these new machines. But you know, beyond all the amazing technology, quantum optics is also just a pure tool for science. Every single experiment with entangled photons isn't just about building a new gadget. It's a way of testing the absolute foundations of quantum mechanics, of pushing the boundaries of what we know about how our universe actually works. So we've gone from seeing light as just a simple wave to understanding it as a quantum tool, something we can use for secure communication, for sensing cosmic collisions, and even for building a whole new type of computer. For almost all of human history, we've used light to see the world. But now we're learning how to use light to write the future. And that leaves us with one final question. What new chapters of reality are we about to uncover?